Okay. Okay, shall we? Right. So today I want to cover two things. So the first half of the lecture will be about inference, which is actually it's a very beautiful topic. It's something that's it's extremely widely applicable. So I would guess that there are, so if any of you are going to work in artificial intelligence, you're going to be doing inference. If you're going to be working on, on bio-related applications, you're going to be doing inference. Almost anything you do, there's going to be some element of inference to it. Well, not for all of you, but probably for 50% of you, that you're going to be at some point dealing with some problems in inference at some point. So what I'll do today is I'll try to give you a sketch of what inference is about. It's obviously a very big topic, but sorry, can we settle down? Okay, so it's a big topic, but sometimes just knowing a little bit about a big topic can orient you in the right direction with respect to it, and that's the attempt today. Okay, so for the first half or 2/3 of the lecture, half of the lecture, and then for the second half of the lecture, I'll go over the second midterm with the following view. So I think that there were at least some of you who came and talked to me, and it was clear that there was something that you missed in the second midterm, which was that so what seemed clear is that many of you were sort of clutching too tightly onto the sort of facts that you had remembered, and not really digested enough to and it seemed to me that the people who came to see me, maybe some of you would have been better off sort of putting that aside and just trying to use your wits to solve the midterm. So my sense was, maybe for some of you, you would have done better if you had, if you had taken the exam, the midterm without being told it was a midterm, and just, somebody had just asked you these questions and said, it's no big deal, these are really simple, can you answer them? Maybe you'd have done even better than you did, right? Without actually remembering anything from the course. So, and I think this is a very important skill, to just have your wits around you while you're working on something. Not just for exams, but in real life later. So, this is something that you should be taking away from this course. So what I want to do is try to emphasize these things, and we'll go over the midterm, talk about them, so on. The associated thing that I said last time, which some of you got, maybe others didn't, is that if you didn't do well on the last midterm, it's not the end of the it's not the end of the world. You have the final, you could do well in that, and I also said that if you do if there's a large discrepancy between the midterm and the final, and if you're then I'll sort of take it into account. So for example, if you're close to a borderline in a grade, I'll try to bump people up who did well on the final, and where the second midterm was sort of unusually low because maybe it counts for this fact that you didn't really understand this thing, but you understand it now. Okay, so that was the backdrop to all this. Okay, so let's talk about inference. Okay, so this comes up in many different contexts. Okay, so inference comes up. So the whole point behind inference is this, that there's something that there's some underlying information that fact that you're trying to infer, and you only get to observe it in a noisy way, right? So your data is noisy. So inference has to do with the fact that you have noisy data. And, so the world is complicated, it's noisy, and you want to look through all this noise and figure out what's on the other side. Okay, so this sort of situation comes up all the time. So of course, it comes up in a situation we already talked about, which is there's data being transmitted over a channel. Noisy channel like a wireless network or with a wire or something like that, or it's stored on a CD. And what do you do? Well, you use an error-correcting code, but then error-correcting codes have their limits. And sometimes what you have to do is, you want to go beyond what the error-correcting code can actually correct for you. Okay, and then you do inference. Okay. It comes up in the problem of control. Okay? So, for example, when you're trying to, this came up in the context of landing a spacecraft on the moon. Okay? So, the actual position of the spacecraft was something that was, there was noisy data about it. So all you could get was noisy data, and based on that, you had to actually steer this craft. You had to know when to accelerate, when to decelerate, when to apply thrusters, etc. How do you solve this problem? So when you don't really know where you are, you just have noisy data about it, and you're trying to navigate. Okay. So we'll talk about how to deal with this problem and how it was dealt with, actually. It comes up in speech recognition. So if you have an iPhone and you have, Siri, but how does it actually make sense of, how does it actually understand what you're saying to it? Well, there's a speech recognition system built in, and that took a lot of effort to build, over many decades of research at various universities and research labs and so on. And eventually, enough is known about how to do that and solve that inference problem that it can actually be included in a product. In terms of, this problem came up in sequencing the genome. Right? And in the dozens and hundreds of experiments in biology that are being carried out today, right? So all the data that one gets in those experiments is noisy, and then there's an inference problem that comes up. And how well you solve the inference problem is really what determines how you do. Right? So it comes up in investing where you have, where you're trying to figure out what's actually going on behind the scenes, should you invest, should you not invest, and you have data and it's all noisy and you're trying to pick out the signal in this data. Okay, so the main thing to take away from this is inference problems are everywhere, right? Okay, so how do we actually formalize these inference problems? So the way we do this is in probabilistic terms. So we say that there's some quantity that we are trying to infer. This is something that's going on behind the scenes. If only we could observe it directly, that would be great. So this quantity that we are trying to infer is a random variable x. So this is a hidden quantity. Okay, it's a random variable x. What do we know about x? So what we know about x is we know what probability distribution x is being picked from. So there's some prior knowledge we have about x. Okay, so for example, if x was the location of the spacecraft, the location is not completely unknown to us, right? We have some idea about where it might be. For example, we might think, well, we know, we are pretty confident it's not under the surface of the Earth, right? We know it's somewhere in the air, it's this many 100 miles away, or this many thousand miles away. It's roughly pointed in that direction, but we don't quite know where, right? So we have some probability distribution which describes our knowledge about where, about this, where this object was. So what we call that is a prior distribution of X. So we have our knowledge about it, and we can translate that into saying, here's a probability distribution which reflects, to the best of our knowledge, where it is. Then we make a sequence of observations. So we might make a sequence of observations, y1, y2, y3, so on, yn. So this is a sequence of observations. Okay. These are noisy. Okay, if we could, of course, if we could observe X directly, then we didn't need to make many observations. We could have done with one observation and we'd know what the value of X was. Right? X is a random variable. We just look at it and we say, this is what it is. But we can't do that. We don't have the ability to tell what X is. So, so we use our measuring instruments, and they're noisy, and what we end up getting is not X, but y1, which is a measurement of X, and y2, which is another measurement of X, and so on. And now, the other thing we know is we know something about the conditional distribution of y sub I given X. Okay? So what we can say is we have some model saying, if the spacecraft was here at this particular point, then our measurement instrument is such that it's going to give us a random location within a ball of radius, 50 miles. Okay, that's something, that might be our model for how our measurement instrument works. So we're given the conditional distribution of what our measurement looks like, given that X is this. Okay? And what's our goal? Our goal is to figure out what's the probability distribution on X, given that we made these observations. So we want to figure out, what we want to figure out is the distribution on X given, something about X given y1, y2, etc. Okay? Maybe the expected value, maybe the variance, maybe the actual just the probability distribution. That's what we want to figure out. Okay, so this is what an inference problem looks like. Now, so we are going to deal today with two very simple cases of this. The first is a toy model around discrete inference, and the second one it has to do with inference of continuous quantities. Okay, so the first one, imagine that you walk into a casino, and then there are n slot machines. There are several. So you have n slot machines. And all these machines are different. They have different odds of winning. So some are better, some are worse. You don't know which one is which. Okay? And for each one, let's say that you observe for a little while, you play on each one for a little while, and afterwards you want to try to infer which is the best one to play on. Okay, so how do you do this? Okay, this is the problem that we're going to worry about. So how do you, given your observations about how these machines behaved in the past, how do you predict which one is a good one to play on? So one way to model this problem is you're given n biased coins. Okay? And you place a bet. So you can choose any coin to place a bet on, and you win win, let's say, $1 if heads, and you lose $1 if tails. Okay? And so let's assume that actually this is a pretty good kind of bet to have, because what you have is you're given that there are n bias coins. So let's say the probability of heads for the ith coin is P sub I. Okay? So for example, let's say that there were 3 coins. Okay, so let's say that P1 was 1/4, P2 was 1/2, P3 was 3/4. Okay, you don't know P1, P2, P3. They just look like coins to you. And you're playing this game. How do you play it? Right? So you don't know from anything. So what would you do here? Well, maybe the first thing you would do is just pick up a coin at random and toss it and see what comes up. Okay, so now if you look at the probability space, let's say this is what it looks like. With probability 1/3 you pick the first coin, 1/3 you pick the second coin, 1/3 you pick the third coin. If you pick the first coin, you have probability 1/4 of heads. If you pick the second coin, you have probability 1/2 of heads. If you pick the third coin, you have probability 3/4 of heads. So the chance that you win is this shaded area, which is exactly half. Okay? But now, what happens if you actually win and you get a heads? Okay? How should you play next? And if you do play the way you think you should play, what's your probability of winning the second time around? Yeah.
What's the point again? Because the probability of the coin that you want with being the 1 3/4 probability is a half.
Right. So if you get a heads, then you know you are in this part of this is where you are. Right? If you flip that coin again, then the chance that you pick that this is the coin you're working with is this area divided by this whole area. Right? Okay? Whereas the chance that you pick this one is that area divided by the entire area. Right? So the probability you win in the second round, given you win first, is going to be equal to what? Well, the chance that you are here, this area is remember, this is 1/3, this is 1/3, and it's 1/4 of a third. So this area is 1/12. This area is half of 1/3, which is 1/6. And this area is 3/4 of 1/3, which is 1/4. Right? So the probability of picking this one is, so remember the entire area of the shaded region is a half. So the probability you pick the first coin, given you win the first, was just 1/12 divided by 1/2, which is 1/6. Right? It's 1/12 divided by this total area. The probability you pick the second coin, given you win in the first round, is 1/6 divided by half, which is 1/3. And the probability you pick the third coin is 1/4 divided by half, which is half. So your probabilities now become different, right? The probability you pick this third coin becomes a half. This one is 1/3. That one is 1/6. These add up to 1. Is everyone clear how I got these numbers? The probability you pick this one is this area divided by this area, right? Because we are conditioning on the fact that we won in the first round. This is the event that we won in the first round. Yeah? Okay, but now, what's the chance we win in the second round? So probability win second given win first is just, well, 1/6 times the probability of winning with the first coin, which is 1/4, plus 1/3 times 1/2, plus 1/2 times 3/4, which is something good. Okay, it's bigger than 1/2. It's just by eyeballing it, we can tell it's something like 7/12, right? No, actually, I worked it out before. Don't, you know. I'm sorry. Okay, so your chance of winning becomes bigger than 1/2. And the point is, you know, if you keep doing this, so let's say that you won the second time as well. And now you figure out what's the chance that you would win again if you won the second time. And the chance would go up again. Right? Okay? And of course you could work out, given that you had a certain streak of wins and losses so far, what's the best thing to do? Okay, so, but this is the kind of reasoning we want to do. Now, let me go through one more step of this, where we'll do this in generality, and then we'll sort of stop there because, you know, we can keep going as far as we want, and we want to stop somewhere. So we'll just do this one step in generality, and then you'll see that you can actually work this out if you wanted to, in, you know, for a number of steps. Yeah.
When you're saying the probability increases each time, is this when you're sticking to the same coin?
Yeah, so, you know, what I'm saying is, suppose that you got a heads the first time, then it's better for you to stick with it. Suppose you got a heads the second time as well. Okay? Then the chance that you get a heads the third time would be even higher. Because you know, if you've seen heads, you know, several times in a row, the chances are much more that you were picking, you had this coin than that you had this coin. So your distribution starts skewing in that direction. And so your chances of winning start skewing towards this particular coin. So in general, what will happen is, you know, suppose you got lots and lots of heads, right? Then over time, what you'll end up doing is you'll start favoring the coin which has the maximum bias. Okay? And so you can come up with a strategy according to which you should play so that you end up, you know, picking the best such coin. Okay? So you know, all we'll do here is just work through the first step of this process. And then, you know, inference itself is a big topic, but you can sort of imagine how it goes, you know, the rest of it. Okay, yes. Sorry, there was a question, yeah.
Can you say again, like, how did you get the probability of winning the first round?
How did I get the probability of winning the first round? You mean, how did I get that the first round, the probability was 1/2? Yeah, so, well, what I did was I said I'd pick each coin with equal probability. So there were 3 coins, each with probability 1/3. So this was the probability space. That's the first coin, second coin, third coin. In the first coin, you won with probability 1/4, second one 1/2, third one 3/4. Right? So the probability of winning is just this area. And by symmetry, you can see it's 1/2. So it's 1/3 times 1/4 plus 1/2 times 1/2 plus 1/3 times 3/4. So if you add it up, it's 1/2. Yeah.
What if you get a tail? Is it better to switch or stay?
Yeah, then it would be better to switch. And then you want to pick one of the others with equal probability. And so, yeah, and then it'll get complicated after a little while. How do you deal with a general strategy? And so you'd have to you'd have to do these calculations and figure out what's the best choice. Okay, and that's the whole subject of inference. So, what we are doing is biting off a little piece of it, but sometimes that gives you the best picture of how to move forward. So you avoid the complications and you see the big picture, and then, much later when you've decided which way that you're going to go into inference, then you realize how hard it is. Okay? Oh, yeah. All right, so let's see. Let's work through some of the details. So let's say that the probabilities of heads were P1, P2 through P sub n. These are the n coins. So the probability y1 equal to heads. So this is the first toss. And the coin is the ith one, right? So and we pick the ith coin is just so we pick the ith coin with probability 1 over n, and the probability we get heads is p sub I, so it's p sub I over n. Right? So the probability yi equal to heads altogether is just you can work this through with conditional probabilities if you want, or you can just work it through intuitively. Okay, so if you just work it through intuitively first, then basically all you have to do is you have to say, well, you picked each one with equal probability, so the probability that you'll get a heads is just summation pi I equal to 1 through n divided by n. Right? But how did we get it? Well, we said so it's a probability yi equal to heads given x equal to I times probability x equal to I sum over all I. Right? So this is the total probability rule. Right? Right? Is everyone okay with this? So this is the probability yi equal to heads and x equal to I. But now you just sum it over all I. And you get the probability y equal to heads. Okay? Now what we want to do is we want to figure out what's the probability y2 equal to heads given y1 equal to heads. Okay? So we already made our first observation. It was a heads. Now we are sticking with that same coin, and we want to know what's the probability that the second flip is a heads. Okay? So again, we can write it as summation of all I of the probability x equal to I given y1 is heads times probability y2 equal to heads given x equal to I and y1 equal to heads. Okay, so let's try to make sense of this. I'm sorry. Can you let me write this again. Okay? So what are we saying? Again, now we are again doing the same rule, the total probability rule, except what do we know? Okay, so we want to know what's the, okay, so maybe let me write this again in this form, just okay, so let me write it back in that form because maybe you can see it better. Probability, we want to know what's the probability that the second toss was a heads given. So what do we know now? Well, we know that the first toss was a heads, and we also condition on the fact that x equal to that we actually chose the ith coin. Okay? And now we'd have to multiply it by the chance that what we are conditioning on is actually true. So the probability y1 is heads and x equal to I. Right? And if we sum over all I, then we'd get we'd get the probability that y2 equal to heads given y1 is heads. Okay, so how do we figure out these probabilities? Well, this probability we already figured out. What's the probability y1 is heads and x equal to I? Well, this is just pi divided by n. What about the second probability? How could we possibly figure this out? So now here's where we use something very interesting. What we use is the fact that once you condition on the fact, so the probability y2 is heads given y1 is heads, this is not something we know how to figure out, right? Because if I tell you that the first flip was a heads, it makes it more likely that the second flip was a heads, right? That's the whole point of what we are doing. But now we are conditioning not only on the fact that the first flip is a heads, but also the fact that the coin is the ith coin. Okay? Once I condition on the fact that I'm using the ith coin, where probability of heads is pi, and I tell you that the first flip was a heads, what does it tell you about the second flip? Nothing, right? Because that's the point of coins, right? The whole point of doing a coin flip is, if I tell you this is a coin of bias 3/4, here, let me flip it for you. I can flip it. It came up heads. And now I ask you, what's the chance that the next time I flip it, it'll come up heads? Same, 3/4, right? So once I condition on this, the information about what happened in the past, it just goes away. It's completely irrelevant, right? The future is independent of what happened in the past, once I tell you which coin it is. So we can figure out this conditional probability by just dropping that, because it's irrelevant. I know which coin it is, so I know what this probability is. So that's the main step in this inference problem. Once you condition on your model, your past disappears from the conditioning. Okay, and now everything else is sort of straightforward. So now you just simplify it. It's summation over I. What's the probability y2 is heads given x equal to I? If it's the ith coin, chance of heads is p sub I. So you get p sub I times p sub I over n. Okay, so you get the chance of heads is, the second time around is summation pi squared over n. What about the first time around? Well, the first time around, the probability of heads was, this was y1, was summation pi over n. Okay, so what you can show is that this quantity is always less than or, it's always greater than or equal to summation pi over n. Sorry. No, wait. What do I want to say here? Um, um, hmm. Sorry, I'm making some calculation error. Let me just I can't figure it out online. So, oh, I see. I forgot. Oh, sorry. So. Uh, um, oh, I see. Oh, I'm sorry. Okay, so do you mind if we rework through this part, because I think okay, so let's try to figure out what's going on. So remember, okay, so let's go back to this formula, right? So this was the law of total probability, where we were saying, what's the probability y1 is heads? It's the probability y1 is heads given x equal to I times the probability x equal to I, right? So this was the probability y1 equal to heads and x equal to I summed over all I, meaning we had all up, we had our three possibilities, x equal to 1, 2, 3. For each of them, we had the probability that we had a heads. And this is saying that the probability y1 is heads is this area plus that area, where these are the three such terms. Now, if we do the same thing for a second coin flip, we want to know what's the probability y2 is heads given y1 is heads. So what we do is the same thing, where we say, okay, now let's condition on, let's do this. This is our event. Let's condition it on x equal to I. So that's what we did here. We condition on x equal to I. And now what we want to do is we want to compute what's the probability x equal to I under these circumstances. So now we take it times probability x equal to I given y1 is heads. Right? So we are working under this condition that y1 is heads, and we are doing the same thing we did before. So probability y2 is heads is going to be probability y2 is heads given x equal to I times probability x equal to I, right? Except all this is happening under the conditioning y1 is heads, right? Okay, so now, okay, but what was the probability x equal to I given y1 is heads? Okay, so this is probability y1 is heads and x equal to I, which is p1 pi divided by n, whole thing divided by sum over I of the probability x equal to I given y1 is heads. And so you'll get summation pi divided by n. Okay, so instead of this times p1 divided by n, it's that. And when you cancel that out, you get summation pi squared divided by summation p sub I. Yeah, sure. Okay, so it's summation pi times pi divided by summation of pi times pi over n divided by summation pi over n. Okay, so you cancel the n's. It's pi times pi divided by summation pi. Okay, but when you add that up over all I, you get summation pi squared divided by summation pi. So that's the probability of winning in your second round. But the claim is that this is bigger, always bigger than the chance of winning in the first round, which is summation pi over n. This is by Cauchy-Schwarz. The fact that this inequality holds is basically Cauchy-Schwarz. Which, if you know about, it's fine. If not, this is just an inequality. It just shows you that, that always your chance of winning in the second round, if the first event was favorable, is always going to be higher. And so you should let your bet sort of run. Okay, so that's it as far as this particular inference problem goes. Maybe let's take about a minute break, and then I'm going to quickly tell you about Kalman filter, and then I'll try to make it very brief, very short, and then we'll talk about the midterm for 15 minutes. Okay. Okay. So shall we resume? Okay. So let me tell you about for 10 minutes, 15 minutes, I'll tell you about, this inference problem in a continuous domain. Okay? Can you please? So there's this inference method, which is called the Kalman filter, which has been extremely influential. So this is an extremely influential way of doing inference. This first came into prominence during the Apollo moonshot. So basically, Kalman, who invented this way of doing inference, visited NASA in the year or two leading up to the moonshot, and he showed them he saw that they had this inference problem in terms of navigating the spacecraft and with the rocket, and he showed them this Kalman filter, and they incorporated it in their software. And since then, this has been an extremely influential piece of work. So it turns out that actually Kalman was not the first to do this. There were a couple of other scientists, Thiel and Sperling, who did this before Kalman. I think they were in Europe somewhere. But of course, the thing that they did not do is they didn't go and visit NASA. And so it's called the Kalman filter. Okay, so what's the problem that the Kalman filter solves? So, this is just one example, example of the problem it solves. But here's the problem it solves. So imagine that your location, the location of your spacecraft, is, at various times, is this continuous random variable, right? So let's actually plot it out in time as the spacecraft is going along, and maybe it's maybe this is its location over time. Okay, so this is your observation x1. So it's at this place. This is your random variable x2. It's at this place, right? So let's say it's a one-dimensional variable. This is the distance. This is how it's sitting in a one-dimensional space, and of course you use this in many dimensions, but in 3 dimensions. But it's all the same thing. That's x3. That's your third, and so on. That's x sub n. That's where the spacecraft is at time n. So it's moving. It's moving slowly at first, then it moves fast, then it slows down again. Okay. So what this corresponds to is what your spacecraft was doing was it started from here, and then it moved along. It moved slowly, and then as it took off, it speeded up, and it went very, very quickly, and then it started slowing down again. Okay? Now, what you get to see is y1, y2, y3, and so on up to yn. Okay, these are measurements. So remember, this is how the spacecraft was actually moving, and what you actually get to see is these y sub i's, which is as noisy measurements. So in fact, what you get to see is this kind of jiggling measurement. So your y1 is this thing, y2 is that, y3 is that, yn is that. Right? So what's happened is that we've added a random variable z sub I, which is our noise random variable, which says, even though the position was that one, our noise sort of in the measurement says it's actually the farther away or closer than we thought it was, than it actually was. And what we want to do is we want to apply a filter. So what we want to do is we want to do inference. And given these values, so this is what we get to see. The blue points is what we get to see. The black points is what we want to infer. And so what we do is put this through this filter, this inference filter. And what we end up with is that sort of curve, where this is x1 bar, x2 bar, xn bar. Okay, so in fact, what we want to do is get rid of this noise Okay, so what are we going to use to get rid of the noise? Well, what we're going to use to get rid of the noise is the fact that our random variable doesn't change very much. It's continuous. The rocket, if it's at position x at this time, in an instant it won't teleport and get to a different part of space. It's just going to move a little bit. Okay? On the other hand, the other thing we know is that this noise is sort of random. And we'll assume, when something is random, what do we assume it is? Gaussian. Great. Yeah, so that's what we'll assume. So we'll assume this random variable is Gaussian with mean 0, okay, and some standard deviation. So this is Gaussian or normal with mean 0 and standard deviation sigma sub z. Okay? Or variance sigma sub z squared. Okay, we'll also assume that our initial starting point is normal with mean 0 and standard deviation sigma squared. Okay? And for the purposes of what I'm going to show you, I'm going to assume that this, our spacecraft was actually a very stable one. So it starts off at x0 and it stays at x0 all the way through. Okay? We're just dealing with a noisy measurement. So what in what I'm going to do, in actual fact, the way we'll model this the spacecraft is it starts at some point and then it slowly changes where it is. And the changes are also according to some normal distribution. But for the purpose of this lecture, I'll just assume we start at position x0 and we just keep staying at x0. So x1 equal to x0, x2 equal to x0. So we'll just assume x1 equal to x2 equal to xm. So, our spacecraft is stationary, and we just do a bunch of measurements on the same stationary spacecraft. So we do a measurement y0, y1, y2, and so on. And what we want to do is get a better and better idea of where the spacecraft is located. Once we can solve this problem, solving it when the spacecraft is moving is a piece of cake. So, it just gets a little more complicated, but the ideas are still the same. Okay, so here's the problem we want to solve. The location of the spacecraft is x. What we get to see is y equal to x plus z. Okay? So x was distributed like normal, mean, mu, sub x, standard deviation sigma sub x, or variance sigma sub x squared. Z was distributed normal with mean 0, variance sigma c squared. Okay? What we want to understand is given that we got to see y, what's the distribution of x? So given y, what's x? So here's a picture of what the situation turns out to look like. So see, here's mu sub x. This is what we know about where the spacecraft should be. We think it's here, but we also know that it's distributed like a normal distribution, right? With some standard deviation, sigma sub x. Now we make a measurement, and suppose our measurement tells us that it's at this location. This is what, so we are told that our measurement came up with this result. Okay? Now, where do you think the spacecraft is? Well, it depends upon how good your measurement result is, right? So if your measurement result is extremely good, if it's very, very accurate, where's the spacecraft? It's at y, right? You don't care what your original notion of your probability distribution was. If you saw the spacecraft here, that's where it is, right? I mean, if you really trust your eyes and this is where you saw it, that's where it is. It doesn't matter what you thought the probability distribution was. Okay, it had some probability of being here. It ended up being here. That's all there is to it. Now, what if your observation was really terrible? You couldn't trust it at all. Then where's the spacecraft? It's exactly that, right? So if you can't trust it at all, or you made the measurement, and as far as you're concerned, it gave you no information at all. Right? Now, if your measurement was of a different kind, where you could say, if it tells me it's in that direction, it must be in that direction, right? That's a good measurement because it told you something. It actually told you it's in the opposite direction, right? So you were just not listening carefully when it told you that. But a really bad measurement is one which doesn't tell you anything. So if it doesn't tell you anything, then afterwards you know that this is really, that's where the spacecraft is. Now, what happens in the intermediate situation, where it gives you some information, but it doesn't tell you too much about it? Where the measurement is noisy, it has some standard deviation, so you know that, if all you knew was the measurement, then you would say, well, it's roughly here, but there's a standard deviation, so you'd have a Gaussian curve here. And now you have two pieces of information. You know, on the one hand, that it was supposed to be at this place with this kind of standard deviation. On the other hand, you know it's at this place with some other standard deviation. So you have two pieces of information, and you're trying to put them together. So it turns out that when you put them together and you run through the calculations, something very beautiful happens. It turns out that conditioned on y, x is normal. Okay, it's still a Gaussian. Its distribution is still a Gaussian. It's a Gaussian with mean mu1 and standard and variance sigma 1 squared, where mu1 is some linear combination of mu sub x and y. So you have some mu1. Okay? That's the mean. The mean is somewhere in the middle of the two. And the standard deviation, or the variance, is also somewhere in the middle of the two. It's 1 over sigma x squared plus 1 over sigma z squared. Okay? And what's A sort of tells you, the two things are fighting each other. The variance of x and the variance of z fight each other to figure out what A is. So A is sigma z squared divided by sigma x squared plus sigma z squared. Okay? It's beautiful. I mean, that's what it is. So now once you know this, okay, so what can you do with this? Recursion, right? I mean, that's what you do. So you started off knowing that you knew something about the spacecraft. It was, you knew that its mean position was this and the variance was that. Its distribution was Gaussian. And now you made a measurement. And you can, the result of making that measurement, even though it was noisy, now tells you that the location is still a Gaussian with a different mean, different variance, which takes into account completely the measurement that you already made. Okay? So now you're back to the kind of situation you were in before. You still know that it's a Gaussian with mean something and variance something. If you make another measurement, you can incorporate that in the same way. And you can keep doing this for successive measurements. Right? Because you started with knowing it was a Gaussian. After incorporating one measurement, you still know it's a Gaussian. So you incorporate another measurement, you still know it's a Gaussian. So you can keep updating the information you get from each measurement. So this is the Kalman filter. Okay, this is what I'm showing you is a cartoon of the Kalman filter. If you work it out in full detail, it gets a little complicated, but nothing changes conceptually from this. So this is the entire concept behind it. Okay? Okay, so let's see. Do we have about between 15 and 20 minutes? Do you want to talk about the midterm and how to? Okay, so let's do that. Everyone okay with this? Yeah? Okay. Okay, so let's talk about I'm going to go through some of the questions in the midterm, and I'll go through them a little quickly, and if you really want me to stop at one of them, we'll stop at one of them. I'll skip a few. Okay? So here's one of them. Let me know if you want to skip this. I'll keep going on, right? Okay, so this one said number of bridge hands with a 6-3-2-2 distribution. Okay, so now how do you think about this? Well, so the way you think about it is, well, so maybe it was the 6 cards. Oops. Maybe the 6 cards were all hearts. So all these were hearts. And maybe the 3 were all, no, they were spades. Okay, and now the 2 and the 2, there's, you can't really tell which is which, right? Whether, you could call this one clubs and that one either you could call this one diamonds and that one clubs, or the other way around, and it doesn't make any difference which one is which, right? That's the same hand. So what does it take to so in order to determine this hand, all you have to do is determine which suit is this, which suit is this. So there's 4 times 3 ways of doing this, and then you have to pick out the 6 cards, 3 cards, 2 cards, 2 cards from those suits, right? So it's 13 choose 6 times 13 choose 3 times 13 choose 2 times 13 choose 2. Okay? So let's keep going from there. Let's talk about this one, because this was maybe a little tricky unless you thought about it on the spot. Right? So it was asking how many increasing sequences of k numbers, how are they taken from this? Okay? How many ways are there of picking k numbers from this which are strictly increasing? So the important thing here to notice was, okay, so this was, here you had to really think a little bit. It was one of those aha moments, right? Because what do you do? Well, you could say, well, there are n choose k ways of picking k numbers. Okay, but now how do you order them? So once you pick the k numbers, you have to sort of notice that there's only one way of ordering it, which will be increasing, strictly increasing, right? So okay, what's the point of all this? The point is, if you were trying to solve this by formula, you weren't going to get it, right? So if you came to the exam sort of armed with a formula and you were just doing pattern matching and you were saying, how do I apply this formula? Right? That wasn't the way to do it. What you had to do was you had to apply your understanding of the situation, right? And so this is the sense in which I meant that if you came to this exam sort of too prepared and too, sort of too much in a rut, that was a way to, that would get you something, but it wouldn't, it would actually steer you away from the answer in some of the other cases. Whereas if you just sort of, approached it in a much more loose way where you were actually thinking, that was the way to approach these problems. I'll show you more about this. You'll see this in other cases as well. So for example, this one. Again, you're counting the number of x such that 4 times x equal to 21 mod 41. These are questions that you actually solved before, right? For example, you solve the equations like this, 4 times x equal to 21 mod 41. And you solve them by doing what? By dividing by 4 or multiplying by 4 inverse mod 41. Right? You know the inverse exists because 41 is a prime. So there's only one such x, right? Except that this was given to you in a different context, right? But again, the point is that you want your knowledge to be not too brittle, because when you apply it in real life, nobody is actually going to say, well, remember, this is a question about modular arithmetic. We are solving an equation. This is how we're going to do it. When you solve it in real life, it's there in front of you, and you just think, right? So if you go in armed with a formula saying, well, whenever you're doing counting, you apply, this particular formula, that's not the way to do it. You go in there sort of knowing that you've got to think your way through the answer, right? And actually, once you start thinking about it, it ends up being an easy question, not a hard question, right? Whereas if you go in there trying to pattern match and say, there's a formula, let me try to apply it, it ends up being a difficult question, right? So that was that's what these questions were doing. I'll skip this for the moment because, if we have time, I'll come back to it. Let's talk about this lines question, okay? Because again, this was another question where sort of everybody should have got it if you were just, if you just came into this exam without thinking, without even knowing anything from, well, maybe you needed to know a little bit about modular arithmetic, what mod p means. But other than that, you could just do it barehanded, right? So what was this? It was saying, we are selecting a random line, and we want to know what's the chance that it goes through a given point. So here's our question. Here's x, y. We want to know if we pick a random line, what's the chance it goes through x, y? Right? Well, okay. So how do you think about it? Well, a random line is going to pass through at x. It's going to pass through a random place, right? And so the chance that it goes through exactly this one is going to be 1 over p. Right? What's another way of saying it? Well, another way of saying it is, you remember how, a line is determined by 2 points. So you could say it's x, y, and x prime, y prime. Right? So you could say, what's the value at x? What's the value at y? This is going to uniquely determine the line. And now, how many ways are there of picking lines? Well, there are exactly p-squared lines. Of these p-squared lines, how many pass through this point? Exactly p. So p pass through the line. There are p-squared lines. So it's 1 over p. Right? But to do this, you had to do nothing complicated. You just had to think about so this was a conceptual question. It was intentionally made to be not complicated, so there wasn't a complicated answer. It was just to make sure that you understood the basics. Then this, even if you couldn't solve the previous one, maybe you could solve it after doing the second one, right? Because you could say, well, what's the chance it goes through x1, y1, x2, y2? Well, again, there's exactly one line that goes through that. How many lines are there altogether? Well, you could have any point with x1, any point here, any point here. So there were p there. So it's 1 over p squared. Okay, the third one was again, it was again a question where, actually, it was a question where you had to be more on your toes than the first two, because there wasn't a formula at all to solve this. Because now you were told, what if you were given 3 different points? Now, again, this is something that, you probably, if you were asked this without it being on an exam, you'd probably get it right every time. If you were given 3 points and you were asked, what's the chance that a line goes through them? Well, the answer might be 0 because the points are not on a line at all. Right? So if they are not on a line, you could have 3 points which are not collinear, and then the chance is 0. And if they were on a line, then of course, as soon as there's exactly one line that goes through them, so the chance would be either 1 over p squared or 0. Right? So again, what was being tested was that you really understood what this topic was about. So do you see the difference? maybe again, let me do it by analogy. You know, when I talked about the Kalman filter, we didn't do any calculations, right? We could do the more complicated case where your initial distribution was given, and then you said x0, x1, x2, these are all different, and you're given these measurements, and how do you solve it? So the calculations get more and more complicated, but conceptually everything stays the same, right? And so all I was concerned with in many of these questions was, did you understand the concept? You know, rather than could you actually carry through the complicated calculations? Both are actually useful, both are important. But in order to carry out the complicated calculations, it's important that you actually understand the concept behind it. And so here, what I was trying to do was make things so simple that you didn't have to do anything hard in terms of calculations. You just needed to, you just needed to show that you understood the concept behind it, right? Which is why it was important that you go in there without sort of carrying around these formulae and seeing whether you could match it up. You really needed to think and see that you understood what was going on. So does this make sense? It's sort of a skill to. I'm not trying to criticize or something. I'm just trying to say this is something that would be it's an important thing to learn. It's something that will stand you in good stead later in your life. You know, this is a course where, the advantages of thinking conceptually are really stark. You know, it's very easy to tell when you're thinking conceptually because you just see it completely. In the real world, it's much more noisy, right? So there's a real reward to thinking conceptually, but there are many other factors that come in. Here we can isolate it completely, so you can actually learn this skill. And it really makes a big difference. And it's an important skill to have. There are other important skills too, which you should learn, but you should learn this one too, right? So that was the point here. So let me try to say one last thing, which is the graphs question. Maybe I have 5 more minutes, so let's just do this question, and then if you want me to talk about other things, we can, but let's do this and stop. Okay, so this question was about graphs, and what it said was, okay, so maybe there were 2 things going on here. One is you had to understand notation to follow the definition, what was being told to you. So you were told that there's a certain kind of undirected graph, which is called a bipartite graph, where the vertex set is the union of 2 disjoint non-empty sets, V0 and V1. Okay, so it's one of these things where at some point you get fluent in this. Hopefully you already are, but okay, so you have 2 non-empty sets. There's V0, there's V1, they are distinct sets, and the edges consist of all pairs UV, where U belongs to V0, V belongs to V1. So meaning for every vertex, U here and V here, there's an edge. What that means is if there are many vertices here and many vertices here, then everything is connected. Right? So the graph is a complete mess. Everything here is connected to everything here by an edge. They're adjacent, but there are no edges between these vertices, these vertices, these vertices, and so on. Right? So now what the first part asked you to show is that every complete bipartite graph is connected, meaning there's a path between every pair of vertices. Okay, so if you look at this, you're thinking, well, you want to know that you can get from any vertex here to any other vertex. Well, this should be obvious, right? Once you look at it, it's obvious, because to get from any vertex here to any vertex here, there's a direct edge. To get from any vertex here to any vertex there, well, you can just hop across. So that's all you needed to say. That if you're on opposite sides, there's a direct edge by definition. If you're on the same side, well, you have a common neighbor. Okay, so that was the first part. The second part said, okay, this gets very tricky. Actually not, it's simple, so let's see. Okay, so it said, show for any graph G, either G or G complement must be connected. So what's G complement? G complement is this, it's the same vertices. So here's an example. So Here's a graph G. That's a graph G. What's G complement? You just connect those, you put those edges which were missing in G. So you put this edge in, that edge in. Right? Anything that was missing, you put it in. So now what does the question say? It says either G or G complement must be connected. So how do you see this? Well, so you say, well, suppose G is not connected. Right? So if it's not connected, that means it has some connected components. Right? So let's say that this is one connected component here. And then there's the rest of the graph. Okay? So now, what can we say about G complement? What we can say about G complement is, let's call this V0. Let's call all of this V1. What do we know about the edges in G complement? Every vertex here is connected, has an edge to every vertex there. That's it. So we are done by the first part. Okay? Okay, so let me try to clarify again, right? So ideally, what you'll take away from this course is that, it's worth, when you're thinking, when you're trying to solve these problems, it's not that it's just a bunch of, a bunch of symbols that make no sense, and oh my God, they give you a headache, and you look at them, and they swim in front of your eyes, and it's all a disaster. That's not what this is supposed to be. There are actually pictures behind all this, and there's a way of thinking about it. And in fact, if you bring to this, and it's a matter of having some faith, because you can do it. It's something that you should really try, where you, instead of clutching on to the formulae and trying to work through them, if you just try to let go and see if you can navigate this just by, that it all makes sense and there are some ideas behind it, right? If you try to do that, you might find that it actually is that you are really good at it, that it's fun, that it's easier, it's better, you get more points, it's all. Okay, so just try it. Okay.